Our first talk today is by Tapasi Ghosh, who is a scientist at the Green Bank Observatory. She spent many years of her career at the Arecibo Observatory, where she was the main contact for all of the VLBI work at Arecibo. And now she's been doing some VLBI work at Green Bank as well. So she'll be talking today about the role specifically of large single dishes in VLBI or very long baseline interferometry. Thank you, Tapasi.
Thank you. Good morning, everybody. So this is our outline. So many of you might have already used interferometry, the VLA and VLBI, etc. But because this is a varied group of people, I'm sort of going to start with the basic concept, just a very quick review, and then of interferometry. Then we'll mention what is VLBI and single dish perspective, and a few scientific results. Okay, so let's see. It's not moving. That is a problem. Okay, here. So, oh God. I'm sorry. This is taking its own. This is sort of going at its own speed. All right. Okay. So on the left-hand side here, I'm showing a picture of a experiment that many of us have done at the optics lab. This is the Young's double slit experiment, which basically shows interference fringes. So there you have a monochromatic light source and a screen and two pinholes through which slits through which the light comes, and then it produces interference pattern at a distant screen. So here they produces where there's no phase difference between the two incoming incoming rays. You have constructive interference, and then when it is 90 degrees, you have destructive interference. And the fringe spacing here, so the spacing between light, dark, and the bright fringes is lambda by d, which is where the d is the separation of the two slits. Other concept that we use here is called fringe visibility, which means how clearly you can see your dark and bright fringes. So that's defined by intensity maximum by intensity minimum divided by the average intensity. So radio equivalent of that is when two radio antennas looking at the same sources and the same source, and then you bring down the signal from the two antennas and you basically multiply and integrate, which we call as correlation. So when you form a correlation here, what you will see is your recorded signal will have a cosine variation with as a source, right, as Zen said. So the phase difference between the two incoming rays at the two stations or two telescopes is basically this extra path length that one of the rays have to traverse, and and this is basically determined by the actual physical separation of the two antenna. So now, and what you can do then is you can split the signal here, and you can add an extra 90-degree phase to signal coming through one of the channels, and you can record the sign correlation of the signal also. So basically, then you can determine a complex correlation complex correlation value at the end of this process. So all of that is put into this little box here. How well you see the, how well you resolve a source now, or the fringe spacing in this case also, it will be determined by separation of the two antenna. And that basically determines what resolution power you have. Instead of the resolution defined by the size of a single dish, now it's defined by the separation of the two dishes. I'm having trouble moving through this. Okay, no.
You might want to click the pause button. I think if it says play, then it moves at whatever pace it wants. So I would just use those left and right ones.
Okay.
Or if you want to switch out into the other.
That's good. No, I'm fine now. Yeah, I'm fine now. Okay, so all right. So what's happening is right now, looking down from the source to the, looking down from the source to the two antenna, what happens is this: as a source rises and sets, the separation of the two telescopes, the baseline vector, as you call it, that, as seen from the source, basically traverses a elliptical path on a perpendicular plane on Earth. Okay, and the two components, one along east-west direction and the other along north-south direction, these two components of the baseline vector, these two are called U and V. So the area that this baseline vector covers, this is called the UV plane. And effectively, what you are synthesizing by looking at a source this way is an effective telescope, which is basically determined by the UV coverage of your baseline vector. Now here we've shown only two antennas. In principle, you can have multiple antenna, and so you can affect your synthesized telescope this way by covering different areas of U and V. And how well you cover and how big that is, that determines how is your beam pattern going to be, and how well you resolve a source and how well you map a source. Okay, so so people talk about UV coverage, then you have to basically, when you think about interferometer mapping, then basically you need to see for how long you're going to observe, what is your array configuration, where are all the antennas, is it going to give you enough resolution, is it going to give you a good beam. These are the consideration you think of when you're thinking of an interferometer and your observation. And so far, we only talked about point source. Now, normally, most of the sources that you want to map will have a brightness distribution in the sky. And how will that look like in my response, in your response to the interferometer? So every point in this extended source, that will form its own fringe pattern through your simplified interferometer here. So the telescopes in this picture are pointing at this point, which we can refer to as phase center, because that's where both the telescopes are pointing at. Any other point will have a separation relative to this particular point in the source. So that's called the phase reference point. And then relative to that, any other ray you can imagine will have a different angle, and hence an added extra path, and hence an added phase value to the two rays that will then that will then make the visibility function. So how we determine overall effect that we measure, overall visibility that we measure from an extended source, we basically consider each point separately, and they then are at a different phase. They contribute to a fringe pattern that this system is recording. So each will have a fringe pattern that will have an extra phase, and you add them all together, and this is your measured fringe visibility, or it's called the visibility function. Now, if we look at this equation with a mathematical point of view, then what you see is that this I of sigma, this is basically determining the distribution, intensity distribution in the sky plane. And what we are measuring here is the visibility. If you look at these two, it looks like they are Fourier transform of each other. So we're measuring visibility. Visibility appears to be nothing but a Fourier transform of the intensity distribution. So how do we get intensity distribution then? Because that's what we want. So we want to determine this out of these measurements. We inverse Fourier transform that mathematically, and we then can measure intensity distribution, which is our map or our image. Now, how well we are able to make this map, how well it look like the real source, depends on how well we measure this visibility function. Because this integration, you see, goes from minus infinity to plus infinity. So you need to measure all values of basically B vector, B, the baseline vector, or in the UV plane. And practically that is not always possible, not never possible. So there comes the limitation, there comes various image processing technique, there comes the concept of designing an array, etc. Going on from here, so I'll show you a few Fourier transform pairs here. So if your image was just a point source, then this is in the sky plane. So let's say this is X and the Y, let's say on the sky, the two orthogonal axes, and my intensity distribution looks like a point. And when I measure visibility, this is U and V, I'll measure the same value everywhere. Now taking a cut through a radial direction, which will be the UV distance. This is one looking at the visibility as a single plot, a single line plot. You plot the visibility versus UV distance, it'll be a constant line. So then, you know, Fourier transform of that is a delta function. And so these match up. If you have an extended source, what you determine is basically these concentric circles, and its cross section here will be a sine square by x square, a sin square function. And this is basically what your measured visibility will look like in a hypothetical case where we can measure all of these visibility values, and then we can do a transform from here to here or here to here. We get back the source's brightness distribution. In reality, because we don't have all the measurement, what happens is when we do the inverse Fourier transform, what we end up getting is a dirty image, as we call it, that comes because of our incomplete coverage of the UV plane. And so what we try to do then, we end up with an image like this. So then we just take the UV coverage and make all its amplitude values 1 and Fourier transform it. That tells us what is the effective beam with which the sky was surveyed, or what the beam, how the beam was convolved with the images distribution to produce this dirty image. So we are finding out what the beam was given my incomplete UV coverage. So then we can run a mathematical image processing where we deconvolve this beam out of the dirty image, and we can create a very beautiful, clean radio image of the source. And how do we know this is true? Because then we can use different UV coverages, different interferometer, different arrays of telescopes, and also run different mathematical processes to do this deconvolution. And each time, if we come out with radio structure that looks more or less like this, then we know the actual sky distribution has to be something like this. So some examples of interferometer arrays, VLA here, very famous, 27 antennas, maximum distance 25, the dish size is a 25 meter. And they are laid out in the form of a Y. And this is a low frequency array in India called the GMRT, which goes only up to L band. And it has 45 meter dishes in each of them. VLA works up to 150 gigahertz. I'm not quite sure. Anyway, so it goes from very low frequencies from 80 megahertz to 78 megahertz to in almost getting to the millimeter region. And then here's ALMA. Some of you might have even used ALMA already. It's a fantastic telescope. VLA as well, fantastic telescope. And they run synthesis workshops. If you are interested in learning how to use them, please attend those workshops. So now VLBI. Okay, so the biggest difference between VLBI and linked interferometer is that the dishes here are not physically linked. There is no actual cable connected, unlike in the VLA or in ALMA's case, or even in GMRT's case. In each of these interferometer, the signal is actually brought down on fiber optic cables to a central processing lab where the correlations are all formed instantaneously, real time. In the case of VLBI, those telescopes far apart and on usually very far apart. In this case, they're showing quite far apart on the globe. They are not physically connected. So they give you, by virtue of such big baseline, it gives you milliarc second or better resolution. And even we have worked with antennas in space. Those are Japanese and then Russian telescopes put in orbit, with which GBT worked very successfully with the radiostron. So traditionally, there is no IFLO link between the antennas. But what happens here is very precisely you have to do all the, you will probably, you have attended the talks earlier, that in radio astronomy, we always bring down the signal from the actual observing frequency, RF frequency, to an intermediate frequencies, and then to the baseband, and then we record the data. So all these frequency down conversions have to happen at a very phase stable situation. Otherwise, you will lose coherence. I'm throwing some jargons out here, but what happens in VLBI is what you call the wavefront splitting of the same wavefront that's hitting the two antennas. That same wavefront is split, and then they are brought together to form the fringes. If their coherence is lost, if you don't know which wavefront these signals, each of the signals come from, then you lose your interference. You can never form interference fringes. So that's why all the frequency down conversions need to happen using very, very accurate phase stable local oscillators. And that's why we need hydrogen atomic clocks. each places. So the LO frequencies are generated from the atomic clocks, and their frequency stability is almost 1 in 10 to the power 14, or 13 or 14, that kind of frequency stability you need. And your need for frequency stability becomes more and more stringent as you go to higher and higher frequencies. So once you achieve that, then the data gets recorded on various media. These days they are on disk, and then the disk data is just recorded. Data hasn't been done anything with, just recorded, and then they are sent to a correlation center. So no fundamental difference between VLBI and normal interferometry, just that no instantaneous live physical connection between the two antennas. So they are brought to central processor. These are actually older picture. This is VLBA in Socorro. Right now, you don't have this huge row of tape recorder. It's all very much smaller in size, but hugely improved in capacity. Those numbers, when you're actually proposing to observe, you will have all those numbers at your hand. We have very well documented information everywhere. So VLBA then, can achieve like 0.1 milliarc second at 86 gigahertz, and the operation center is in New Mexico, Socorro. There are 10 antennas all over the US, and one in St. Croix, one in Hawaii. What other areas we have? These are, Arecibo doesn't exist anymore, but GBT still takes part in VLBA in a special array that's called HSA, high sensitivity array. And that's where the need for a big dish come in. So what happens? So far, we were talking about mostly the baseline length and the necessity for high resolution. But there are science cases where you really need hugely sensitive system. As I mentioned earlier, for VLBA, the individual antenna sizes are not that big. Okay, so so to enhance the sensitivity of instantaneous sensitivity, often GBT and phased up VLA is added to the 10 antennas of VLBA, and Effelsberg telescope in Germany, which is also a 100-meter telescope, that's also added. This is called high sensitivity array. When might we need high sensitivity array? The cases where we need it is if we need to observe transient phenomena, which are very short time lived, so you cannot integrate over longer time to enhance your sensitivity. That's one case when you need high sensitivity array. Other cases, if you're looking at a very narrow spectral line, and there you cannot use a broad bandwidth to increase your sensitivity. So sometimes people have the need to do both. They want to observe narrower bandwidth. They also want to take faster data to study, anything that is varying in time. So then the need becomes even more stringent, and these big antennas then contribute immensely to high angular resolution situation. There are other VLBI arrays, one in Australia, and then there's in the millimeter range of frequencies. There's an array, global array, that's called GMVA, where millimeter telescopes are put together in an ad hoc array. Those were not built to be an interferometer, but they are pulled together to constitute an interferometer. And that is organized from Bonn, but GBT take parts in that as well. These are the two space antennas I mentioned earlier. This was the Japanese antenna. It worked between 1999 and 2001. And this radio astron worked for a very long time. And GBT actually sent the provided tracking, also sent the LO information up to the antenna as well when their hydrogen measure clock didn't work. So it was a good collaboration. So AV parameters to think of. I think I touched upon these a little bit, but I give you some of the equations here. First thing is, of course, the resolution. And here, the lambda by B max. This is the separation between the maximally distant antenna. That will give you your finest resolution in the image. So you need to think about that. Sensitivity here. So what is your image sensitivity? How do you calculate that? So you have this is SEFD here is called system equivalent flux density. It's nothing but thesis divided by gain. So it basically tells you if you didn't point anywhere, your system will have some noise because of its own electronics and the background, everything radiating through it. You're not pointing at any particular source, but just letting the receiver system sit there. Your system will register some amount of radio power. And so that equivalent to that is how many Janskis? That is this number, system equivalent flux density. And then you divide that by number of antennas you have in the array by n minus 1, whatever your bandwidth you're using, and your integration time. So immediately you see that if your integration time is limited by a transient phenomena, you're after that FRB, you want to observe that FRB. You don't know when it'll come, and it only lasts for microsecond or something. So you can't increase your sensitivity by increasing this one. So we want delta I to be small. So what is our other recourse then? Then we need to make SEFD lower. One way to make SEFD lower is, of course, you can have best electronics, but you could also have a huge antenna like the GBT. So its SEFD is going to be lower. System equivalent flux density will be lower. So that's where the big antennas, large antennas come in. So this is where I break it down some more. So if you have take two antennas, so total your image sensitivity then is a geometric mean of SAFD1 and SAFD2. So even if one of the antennas you have as a big antenna in your array, there also you make a little bit of gain. Other thing to consider is a nominal field of view. Trouble with there's a little bit of questionable, a little bit of complication in having one big antenna in an array where every other antenna is sort of same size. What is the complication there? The complication is this big antenna will also have narrow field of view, and your overall field of view then is determined by this one big antenna. So how far can you observe on the sky plane? And those are those things you have to factor in. There are ways of observing. There are different methods of combating that, but your field of view will change from a standard VLBI array. If you add one big antenna, you gain in sensitivity, your nominal field of view will change, but you have to keep that in mind. This is a very important resource in planning a VLBI observation. Even this says EVN calculator. EVN is European VLBI network, but everybody uses this. This is also valid for they have all antennas, as you see this as the VLA antennas, and then all the VLBA antennas. These names are VLBA antennas. So GB is right here. Okay, so you can use this tool to select your array, select your frequency, select what bandwidth you're going to observe, how long you're going to observe, and this gives you what is your image noise going to be. So when you put in a proposal for doing a VLBI run, say using GBT or using VLBA, they always require, or they actually advise you to use the EVN calculator and enter this bit of paper, save this calculator output and attach it to your application. so that people checking out the people doing technical review can cross-check your calculation. So that's an important tool. This is another example of what a big dish add. These examples I worked out with the Arecibo on this slide. I haven't made an equivalent one for GBT, but I can, just take it like in its qualitative value. Now you can't use Arecibo anymore. But just take it as a comparison. Suppose you had all these arrays in HSA array, and your image sensitivity, 1 sigma noise would be 3.3 microjansky per beam for these observing configuration. If you remove Arecibo from that, your image noise gets so much worse, okay? And similarly for spectral line observation too. So one big antenna can improve your overall sensitivity very, very much. It can affect it very much. So field of view I talked about now. One thing that current correlation app allows you is that you can record the data, but then what you can do is you can artificially shift your phase center to different parts within your field of view and make a map, make a correlation of a smaller field within your big field. That way, people now observe deep field mapping. They basically create subfields, and there are a lot of technical development there has happened because most of the correlation is now done in the software that's called defects. And because it's all software, it's hugely pliable. You can modify it. All right, I'm running over time, but I think I'm almost done. Yeah, this slide is really important. This is for GBT. So you have to, when you're planning your observation, so you made your VLBI observation request, you got the time, you have GBT in your array, and then it's time to plan your observation. What you have to do, you have to think that big dishes will have a little bit longer slew time. So you have to take into account when you plan your scan. And also you have to run a pointing run. And that pointing scan becomes very, very important as you go to higher and higher frequencies. Plus GBT, to get best performance of the dish, you have to also adjust the dish surface. So you can, there are wonderful technique here that's been developed by a lot of people, with Dave Frere being one of them. So the auto woof and then Lassie related work is also happening. So it can give you wonderful performance at 3 millimeter, but you have to allow about half an hour every hour and a half to 2 hours, depending upon which frequency you're working at, to do the surface adjustment and pointing check every hour. That takes about 6 minutes. So these are the things that one has to remember when you're using GBT or any big telescope. So what you have to do to use GBT in a VLBI experiment? Well, these are the various arrays where GBT can be used. These are more detail about the recorder. Just because we have short time, I'm not going to go into that unless somebody has specific question. I can leave it at that. So the way the mode in the methodology, or just the path that's followed by a VLBI observer using GBT is not the same as GBT used as a single dish. You can, of course, understand that because it has to work as a part of an array. So what you do is you plan your observing, and you create a list of scans. You define your array in a standard format. That's all defined by the VLBA. It's like a key file. You create a key file, you run it through a SCAD program, make sure it works, and it produces scans with all the restrictions that I just mentioned. allowing enough time for pointing, enough time for slewing, enough time for surface adjustment. All the frequencies are fine. You check everything, SCADE runs, you submit that key file to VLBI's location. Then the VLBI analyst, data analyst, or somebody at the VLBI will produce a schedule, and then they will supply that schedule to all antennas that are going to run that program. Okay, they will produce a code that will run at the telescope. So they know, they and us, GBT, we work together. They download a particular Python code, and our operators here are absolutely knowledgeable, and they know everything how to run these observations. As over here, Amber and I, at the moment, we keep our eyes on it. When the observation comes, we basically check out that if everything, the files are loaded at the proper time and things are running fine. If there's anything we anticipate already, we try to work with the PI, correct them, and then make sure the pointings happen, make sure telescope is performing as well as it can, as well as it should, and try to minimize human error, basically. And then when the data is collected here, that goes back to Socorro or to Bond or to Jive, depending upon which bigger array we are participating in. And then they will run the correlation. They will get the additional calibration file. Sometimes we have to work on the calibration file itself because already set up procedures do not work. So then we have to intervene and give the calibration files to the users. And then from there, you take your data into APES or CASA and make your map. I think I will probably should stop there. There were some results that I had here. Maybe I should just quickly mention here. This was one good VLBI result which basically helped locating the repeating FRB, the first repeating FRB. The impressive thing about this was this is like 1 microsecond of data that already produced a map and showed at the time of the burst where this millisecond, sorry, it's a millisecond data. So at the time of the burst, where the signal was coming from, and that led to its identification, etc. So we're very happy with that particular result. And what is in future? I'll end with that. So NGVLA is coming. You probably have heard about that quite a lot. So there will be, in the next 10, 15 years, there'll be a huge array which will have long baseline possibilities, huge improvement in all of the parameters that I talked about. So it's an exciting telescope. So you all will be using that, I'm sure. And in the European side or the world side, there's a SKA. SKA is a lower frequency, and NGVLA will be working from mid to higher frequency. So these two will change the radio astronomical world in the next decade or two and onwards. This was the famous shadow of the black hole image, which was made using a GMVA array and Event Horizon telescope, which was basically using telescopes that are in different locations. That's shown here. So I'll stop here unless people have any question. Sorry, Will, I ran out over time.
That's okay. We are in a break. Just one note about this. There is a planned NG VLBA station in Green Bank as part of that program. So are there any questions for Tapasi? If you have none right now, I think Tapasi would be happy to stick around during this break and answer any individually that you might have. But we will go on a 15-minute break here and come back at 11 a.m. Eastern. So if you do have a question, feel free to unmute yourself or raise your hand and we can call on you. All right, seeing none, we will see you in 15 minutes. And like I said, Tapasi and I will stick around during this break.